solving some fairly complicated shapes with, in parallel with the big mesh. All my examples here are going to be pretty simple looking because I'm doing it in my mini app, which doesn't have the full functionality of the main multiphysics code which I work on. The other good thing about DST is that it is easy to parallelize. The parallelization in MPI was easy, but it doesn't scale well. And so everything I thought about to kind of improve the scalability just thought it was going to be very complicated to do. So that was one of the motivations for trying Charm++. And because this will come up a couple of times, our algorithm has two variations, a linear form and a curved form. The linear approximation is it's faster but less accurate, and the curved one is more expensive. And so those have different performance characteristics. So an example will be useful here. So here we have a box full of some explosives and a hollow cylinder cut through it. If you start a detonation in one corner, it starts off with this kind of spherical shape, and that progresses out. And you can look, all the work is done basically in that red area. So, if you got 4,000 processors trying to work on that little spot, they're not going to have a whole lot to do. So the parallelism is quite poor. As it progresses, kind of works around the cylinder, and then at the end, it completes. And this is really an input into the multiphysics code. What we care about are these lighting times. So the blue is basically time 0, and red is the final time. And as the hydrodynamics code that I work on, advances in time, it's going to be using this information to deposit energy and to work as a kind of a driver for the simulation. So this is done basically once, and it's a pre-processing step. So sort of before anyone can begin stepping through the simulation, they have to run through this algorithm if that's something they're modeling. Okay, and so here's another example showing a more complicated shape. This is in 2 dimensions, and there'll be a movie. So now imagine thousands of processors trying to work on this all at the same time. It detonates right there, that blue spot. The work is going to kind of flow out, going around complicated shapes. You can't really predict when it's going to happen, or when a process is going to be busy, or where the work is going to be ahead of time. So that's part of this. Oh, there we are. Okay. Okay. All right, there you go. So Charm++ being detonated. Okay. So that's actually is using the mini app here. Yes, exactly. Yes. Okay, so I think I've kind of went over the steps already, but the algorithm works as follows. Until you're done, you're going to process all the new detonation sources. So all my examples are going to have a detonation source, like 1 point at time 0. But you can have other ones, more than one. They can be delayed at different times. So the steps are you update the narrowband region from the previous narrowband region. That means basically you add more zones to one end and subtract some from the other end. And then you compute the detonation front, which is a representation of the detonation. You compute a representation of the detonation front, which can be basically in a line or line segments in 2D, or a triangular surface in 3D, and it can be more complicated with a curved definition. You compute distances to that front, and then you compute lighting times, and you basically just repeat. So there's some communication steps throughout here, and so the simplest thing we've done is in our parallelism is start off with a mesh that the application gives you, which is each processor owns some part of the domain, and you compute on that domain. You trade information with your neighbors. So in parallel, there's a couple of places where you communicate. Once you get the definition of the detonation front, there's pieces that you want to trade with your neighbors. You basically run through the same algorithm as normal, and then you have an all reduced to compute the next delta time. And then there's some information on the shared nodes and on the ghost nodes that you need to trade. So the communication steps are interspersed. Okay, so the main problem is this doesn't scale. So as that detonation front progresses, a process is only busy if its domain intersects that detonation front. And so in this example, and the green is not showing very well, say we have a square or a cube you detonate in one corner, and this is representing domains. On 64 processors in 2D, the most you get is 20% busy. That means you always have at least 80% processors idle. In 3D, it's a little better. If you go up to 4,096 processors, you only get around 4% at most doing work. And that's a real problem for scalability. So. Okay, so over-decomposition can help solve this problem. So one simple way to improve the parallelism is to over-decompose. But you have to do it in such a way that you scatter the domains throughout like the problem space. Because if they're all clumped in one space, then that doesn't really help the problem. But if they're scattered throughout, then as the detonation front goes through, a domain will have more chance to be busy because it will, it'll intersect the front more frequently. And so a simple example where we did that, we basically just took a problem, a cube, 512 processors, increased the number of domains per process. With one, it got 17 seconds. It got better and better. It got to 4, and then started getting worse again. And then 64 was worse than where we started. So there was a spot where it was good. 4 seemed to be good for this particular configuration. But there's a lot of, I'm not sure that 4 would be the answer in all cases. That's just for the particular problem I'm solving at this point, with the shape of the domain being very irregular and that sort of thing. Okay, some performance numbers. So let's see. So this is a strong scaling study where we're running with a 256 cubed problem. We over-decomposed it with a round-robin assignment. And I should say that on the last slide. So that's the red line. So the red line is with round-robin. Blue line is with no overloading, so or no over-decomposition. And then if you just use the standard block decomposition, and the way that we're assigning blocks are just close to each other, you actually kind of do worse. And so the way these domains are scattered throughout plays kind of a big role in performance. Okay, weak scaling study. Well, weak scaling study doesn't make a whole lot of sense in this, but what it normally means is you double the problem size, double the number of processors, and you should get about the same time. But for us, you double the problem size. It's going to take longer, no matter how even because of the bad scaling of this. The time it takes is basically from time equals 0. You have to go through some path of zones to get to the final time, and if that's increasing, it doesn't matter how many processors you put on it, it's going to take longer. So anyway, but this slide basically just demonstrates that if you do that, doing over-decomposition is a win here as well. And so and you can kind of see, this is still pretty, I'm sorry, this was time and processors. Last time it was scalability. This time it's time on the time, so time's increasing as we increase the problem size. Okay, so the immediate question is, can you do better with load balancing? And that was something I thought I would try. Easy to try in Charm++. So the principle of persistence doesn't apply here. So the workload is different each time. So basically, at the time when you think you have the process with the highest load, it's going to immediately start being less until finally it's completely idle. So you can't really use that information. So we do know some information about this. We don't know complete information, but we know enough that we can make some estimates about really near-term load. And so I overloaded the UserSetLB function, LBLoad function. And so here's just an example of one approach I tried. Now I'm sure everyone could think of a different approach that might be better. This is just the first thing that I kind of thought of. It was pretty easy to implement. And I can keep on thinking of new ways to improve this. But imagine you have the detonation point here in this corner. This is just a picture at one point in time where the detonation front's here. What I'm going to say is we're going to divide the domains into categories. The ones that are completely burnt through, those are going to be idle and never to be worked on again. So you give them a certain load number, like 0, something very low. Active domains, the ones that intersect with the detonation front, get another value based off of basically how many nodes do they have left to do. And I kind of normalize that by how many nodes they had total. And then there's ones that are nearby, are neighbors of active domains. And they get a certain value because they're going to be busy soon. And then the rest I give another value because they will also be busy at some point. So we don't know exactly when. And so this paid off in some ways. I wasn't completely overwhelmed with the results, but I think I can do better here. I didn't do a whole lot of time, spend a whole lot of effort tuning this, but I'm sure this could be improved. But I did see some improvement. This, just to kind of go over what my experiment was, 4x over-decomposition, 1,024 processors, same problem, 3D cube. This time I used the curved approximation where I actually have more work to do. So that's why this, I think, was a win in some cases. And then I used the initial round-robin placement, and then they would migrate. And then I picked certain parameters, and of course I could tune these parameters a lot. I just tried something that kind of worked. I did a couple examples, and I didn't really try to optimize this. Just picked a few numbers. The basic idea is you want the ones that are busy now to be weighted the most, followed by the ones nearby, and then finally you want to give some good value to the ones that are going to be worked on in the future, because you want them to be kind of separate from other ones that might be on the same process. The frequency is also something you can play with. I picked 50 cycles in some cases, 100 cycles in other times when I was playing around with this. Kind of depends on how many zones you have in your domain. And this is something that probably if I could do this more dynamically, it would work out better. But anyway, so a lot of caveats. There's a big parameter space to study here. I got some improvement. The greedy load balancer turned out to be the best in this case. There's other times when different load balancers were better. So this is some experimentation. Okay, but if you don't have a whole lot of work to do, which is sort of the case with the linear approximation of the DSD algorithm, then the performance isn't quite as good with the load balancing, and then you actually it would give you worse performance. So that's also with the same sort of parameters as before. Yes?
Memory constraint here as well. The inactive domains, they still occupy memory, right?
Yes, they do.
And so I see.
In fact, they still actually participate in some communication to know whether they need to do anything. Okay, so that was the simple approach, basically using domain overloading and load balancing. So there, you can imagine much more complicated approaches. So what I've done so far probably could have been done with AMPI, but the approach of doing domains as you get them from a domain decomposition from maybe the hydrodynamics code isn't the right approach for parallelism in this case. What we have to work with is this really the narrowband that we're modeling. And that's something that's evolving and moving in time. And so if you model that directly with chars that could dynamically increase their size or split apart, that sort of thing, as needed in a dynamic way, you can imagine that might be better. Probably a lot less memory be moved around. Basically, when I migrate a domain, I'm migrating all the memory associated with it, even though that may be a lot more that needs to be moved in a different solution. So that's one idea, and it's an idea for a later time. I didn't get a chance to fully, explore all these ideas with this algorithm. Let's see. But really, the fundamental problem is there's not a whole lot of parallelism in this particular application, even though it can take a lot of time to solve in general. There's just not a whole lot that thousands and thousands of processors can do at the same time. Okay, and another approach was maybe taking advantage of the linear versus curved formulations I described. The linear one being much faster than the curved one. And in fact, to do the curved one, you first actually do the linear one in line, and then do a refinement for the curved approximation. So one idea is if you can dedicate some of the processors to work on the linear approximation, and it can kind of move out as a detonation front ahead of the curved one, you can then know to a very good approximation the lighting times for all the nodes in the problem, and that can be used to feed into a really accurate prediction of when nodes will become busy, because they know what time. Everyone knows the global simulation time, and they know what time they will approximately be reached, and so you can coordinate the workload, I think, more effectively if you take advantage of that. So that's another approach where I think Charm++ would really be a lot easier to implement that kind of an algorithm instead of MPI. Okay, but the topic of this session is interoperability. So the DSD algorithm is truthfully a very small part of a much bigger application. It's an important part, and it's you know, it's run almost every time AL3D is run, but we're not going to rewrite this big multi-physics simulation code, you know, in Charm++ anytime soon. It's, you know, we've been working on it for 20 years. It's very long, very large code. So ideally, we'd like to rewrite just pieces of it in Charm++. And so this DSD algorithm is one thing that we can kind of pick off and use. In fact, it's already written as a library inside of our own code. And so just swapping out the MPI implementation for a Charm++ implementation is quite doable. So I've been experimenting with an interoperability feature that's new in 6.4.0. And I've got this working fully in my mini-app version, although I haven't yet migrated over to the full multi-physics simulation code, although there's no reason why it wouldn't work. So that's worked out very well. No surprises, and it was pretty quick to put in. But there are some challenges. And the first being that the multi-physics application creates a single domain to give to the DSD algorithm. And we just kind of saw, you know, if you do that, you don't have any win over like the MPI. And so you really need to over-decompose to improve the performance. And so I can imagine what you do is you take that domain, you'd break it into pieces with a partitioner, you know, or MEDIS or something like that. But then you would need to, you know, construct like a layer of ghost elements around that, you know, package it up as a domain for use in the algorithm. That would require some communication to know what was happening on the other processors to figure out neighbor communication, potentially. Maybe there's smart ways to do it. But then also, if you break up a domain, they're all going to be spatially located, you know, right next to each other. So you need to then migrate them outward, you know, scatter them, trade them with other processors so that they are in different points of the simulation. So when the detonation front goes through, they won't hit those the chars owned by the one processor all at once. They'll be hit them at different times, so you get better percentage of workload. Okay, and so actually that's one place where I thought the load balancer could work pretty well in this scenario, where they aren't started off with a round robin placement. They actually do start off all together, and so the load balancer knows you know, when and how and where the chars can be migrated. And so if you could just turn that on and let that work, then that might solve this the problem of how to migrate these processors off node or off processor. So that's basically my talk so far. Some final thoughts, though. So I spent about 2 months on this project, basically starting from scratch, extracting this DSD algorithm from our code and rewriting it as a mini app using Charm++, and I wrote in a Charm++ and an MPI implementation of it. The first attempts at this, I tried to keep on thinking in MPI, which it was hard to make the first leap. But once I kind of got into the Charm++ way of thinking, it was quite natural. So I think my second attempt at the Charm++ implementation went very well, and I really enjoyed using the SDEG feature. That was very helpful, and it made perfect sense to me. So that being said, though, the MPI and the Charm++ versions do share a lot of code. So that's actually kind of a big benefit, is that Charm++ isn't a new language. It's it's C++ with extra stuff. So most of the DSD algorithm is identical between the two. Even a lot of the parallel data structures are similar between the MPI and Charm++ versions. So the conversion wasn't too hard to do. And I found the load balancing feature very easy to put into the coding. It was basically writing a function and turning it on. And I had to do a few things with the packing and unpacking, but that was all very easy to do. And all this work would have been significantly more effort and work to do in MPI. So I enjoyed this process and working on this project. Hopefully I'll have time to complete this work and get all the way into the multi-physics simulation code at some point. All right, thank you.
So about the load balancing of your detonation, so couldn't you assign load according to the velocity vectors of the movement through the domain, like the gradient of those, something like that? What are the problems with that?
Okay, could you assign load based off of the velocity gradient? So the load for the whole domain is the number I'm computing. Are you trying to? The question is, though, since you know sort of the direction of the detonation front, and you could probably a different process could probably figure out, I think, that it was going to be the front's approaching it. I think is what you're saying. Yeah. So I think that's right. In fact, I think another you could probably use all sorts of other kind of geometric information to feed into this. Right now, so far I was only feeding in kind of topology information. You could feed in some, even as a rough cut, you could say, I know I'm this far away from the point source, and the farther I'm away, the less likely I'm going to be needed soon. So that would have a lower load balance number, for example. But yeah, I think there's a lot of information you could try here to improve that load balancing. Thank you.
And soon, if it is not in less than the number of cycles that you do load balancing,
then it's as good as zero. So you need to decay that pretty quickly.
Yes. Yeah, that's right.
So I think this thing hinges on the metric for load balance and how you balance the load. I would have thought that doing it more frequently, the base problem, and doing it with refinement strategy, but a good implementation of refinement strategy. I think that the current one has some bug or something should be better, because you want to keep everything to the same place as much as possible and move only the extra work. So to keep the migration costs small. And so I don't know why that didn't work, but I would like to maybe offline talk to you about that.
Okay, sure. And I should say all these numbers are sort of preliminary. This was I didn't attempt to tune anything too carefully yet. I was just looking for the kind of the trends. And so yeah, the frequency at which I did the load balancing is something I didn't play with a whole lot. Probably, I figured too often would be too much overhead, but if you don't do it often enough, then you're just missing. You're just not doing the right approximation. So.
Regarding for with scaling, that you mentioned, do you scale physical parameters of the model, or you scale the parameters in order to just double floating point?
Oh, when I did the kind of the weak scaling, yeah, for that one, is a very simple what I did. Is I took the number of mesh elements in the whole problem and doubled it every time I doubled the number of processors. So the
Does it correspond to doubling floating number of
oh, I see. Yes, it should, because the each zone is probably about equally expensive as any other zone in this problem. It's just that they're all active at different times. So the number of so the total work doubled, but the total time it took to do the solution didn't stay the same, because you have to it's a linearization of this thing where you have to do one step before the other step, and you have to start at the beginning and get to the end, and there's no shortcuts. So even though the total work is doubled, it took more time. No, there's not too much data here. So there's a couple of for each node, there's a couple of fields associated with it. There's the distance to the detonation front. There's a position on the detonation front where you're closest to. So that's like maybe 4 doubles. There's a few other parameters which you store with the node about the current state. It's a handful of things. And then of course you're storing the mesh, but there's not a whole lot of data associated with this. It's mostly there's more computation than. Yes. I think it's not. I think in what the way I'm moving domains around, I'm moving the entire domain, which in some cases is probably more than I need to. it's really just the narrow band information that needs to be communicated around. And so I'm not really treating that as an object to be distributed. I'm distributing on the domains. And so I think a more complicated approach, or a different approach, I should say, where you do just we think about the narrow band as a object that moves rather than domains that are working on pieces of the mesh. Yeah, does that make sense? Right. So I think that you're right. What you're actually working on is this in 2D. Yeah, you're right. It's like this, wavy, kind of somewhat thick, not very thick curve, which is moving, and you know where that's going in some direction. You can divide it into a certain number of processors, or you can have processors waiting for it for that. You can align processors to wait for that detonation front to arrive at them. Anyway, I think there's a lot of approaches here, but okay.
Thanks.
Thank you.